Hello. This is the first video I've made using my new microphone, so you might notice that it sounds a lot better. Hopefully it does. It took me a while to get set up, but I think I have it now. Today in this video we're going to talk about work, and that's the only Rihanna reference I make, I promise. But we're going to talk about work. What is work? Now, we have a kind of everyday definition of work. We know that if I said, if you earned a scholarship, right? You said, what did you do to get this? Well, I worked hard to earn this scholarship. I put in a lot of efforts into studying. I tried hard in my classes. You could say you worked hard. So work in that sense is a little bit different than what we're going to talk about today. Today we're talking about work as a physical property, as something that we can measure, a physical quantity. And let me show you the equation first. I'm going to show you the here. I'll show you the equation you should write down here. All right, this is the equation you should write down. So again, you can pause this and write this down. I'm going to keep on going, so hopefully you paused. Now, this equation is, it's good, but let me show you what the actual, if you look it up on Wikipedia or something, what it will probably say. It will probably say this: work equals F dot X. And it will also have these little, or it might be bold or something, but they'll have these little arrows. Now, I have not done a good job of doing this, but in physics, when you have a vector quantity and you're writing into an equation, you're supposed to put this little arrow. It's like half of a vector arrow. It's just the first top half, basically. So it's the top half of a vector arrow, and you use that to indicate that something is a vector. And if you will look back at our other equations, you don't really have to do this, but you could look back at one or two. For example, you just learned about momentum, right? And you had this equation, P equals mv. Now, if I were writing it out again using this vector notation, velocity is a vector, but you'll notice mass is not, and you would have momentum, which is a vector. Another one real quick, F equals ma. Again, here, acceleration is a vector, mass is a scalar, so it doesn't have. And then when you multiply this scalar and this vector, you get force, which is a vector. So notice that before we kept getting these vectors. Now here I've not put a vector over this because work is not a vector. Which is interesting because most of our things we've been calculating have been vectors, but here work is not a vector. But notice that force and displacement are both vectors. So if you take two vectors and multiply them like this, you end up with a scalar, which is a little interesting. Now, the actual way, when it comes to vectors, remember, vector addition is really weird, right? Because you could have 3 plus 3 and you could get 0 with vector addition. But with work, with multiplication of vectors, there are different types. There's one is called a cross product, and one is called a dot product. We are taking the dot product between these two vectors. And when you take the dot product, essentially you are multiplying the parts that are in the same direction only. So as a vector, you're only multiplying by the component that's in the same direction. And let me try to give you an example here. Let's say you had a let's say I was pushing. Here's a box, okay, and I was pushing on the box like this way. Okay, I'm kind of pushing like here's me. It's a big box, okay. Here's me, and I'm pushing on the box, and I'm pushing this direction. But it only moves in this direction. So if I want to figure out how much work I've done, I'm going to need to take my force and multiply it by the displacement, but be careful. Because the only force that's actually displacing it horizontally is the part of the force that goes in this direction. So I'm not going to multiply it by, just multiply, okay, let's say this was like 10 and this was like 15. Okay, I'm not going to do that. I need to figure out this angle because what I really want to do is I want to multiply it just by this part. That part of my force that's in the same direction as the displacement. Now, you've actually done this before. You've been breaking up vectors for a little bit. And hopefully you'd recognize, okay, I need to figure out this angle. I don't know, let's say it's 30 degrees or whatever. And if you take the cosine of that angle, take 10 times cosine 30, you'll get the same direction. And then you can multiply them together. Now, This is called the dot product. Cross product is really, it's a lot more difficult. When you take the cross product, you actually end up with a vector back out. And it's really strange. You have to use something called the right-hand rule to multiply cross products. But we're not going to worry about that. This is a dot product. And dot products are relatively simple because you basically just, okay, take this vector, project it into the x direction, or just figure out, you know, which of these overlap, and then you multiply those two parts together. Now, I put this on the x-axis, but even if they were different, it wouldn't matter. So in essence, when you take the dot product, you have to use the cosine, and that's where this comes from. So you'll see here that I put cosine theta here. And what is theta? That is the angle between the f and x vectors. But again, if you look this up, you're just going to see work is f, you know, the vector force, the displacement is a vector, and you take the dot product between them. Now, it could be anything, right? Theta could be anything. We're only been looking at cases where theta is 0, 180, or 90 degrees, and that's kind of it. But again, it could be any angle. All right, well, what about the units of work? Let's see what we have here. Again, we'll just do unit analysis. Work is going to be the force times the displacement. Okay, now again, there's that cosine stuff, but, well, cosine theta, what are the angles? Sure, let's look at it. What's the angles of cosine theta? Well, if you take the cosine of an angle, you're going to end up with no units. And remember, it all comes from those triangles, right? If you have a triangle, cosine would be like, in this case, let's say this is like 10 meters, and this is 15 meters, and this is 20 meters. All right, well, if you're going to take cosine of this angle right here, it'd be adjacent over hypotenuse, so that's 10 over 20. So cosine of theta equals 10 over 20. Well, notice 10 meters over 20 meters. Notice what happens to your unit here. Turns out that cosine theta is just equal to 10 divided by 20 is 0.5. Well, that's it, right? I mean, there's no unit left because the meters have canceled. So when you ask, you know, what is the units of cosine theta, it has no units. So in terms of our unit analysis, I really don't care about it. So we basically have force, which is in newtons. Hopefully you Dora the Explorer there. Times the displacement, which is in, that's right, meters. So you get Newton meters. Right, this is newtons and meters are Newton meters, and that's the answer. Work is going to be measured in Newton meters. There is another unit of work that we're going to talk about later, but for now, Newton meters will be fine. Let's look at an example. Actually, before we do that, let's look at this. Okay, in Greek mythology, Atlas was a titan who held the sky on his shoulders. According to the physics definition of work, Atlas does no work. Agree or disagree? Now, you can look up pictures of Atlas. He's supposed to be holding up the sky, the heavens on his shoulders. And there's a funny story about Hercules. One of his labors is basically he has to get these golden apples, and Atlas is the one who can get them. And so Atlas has to hold up the sky. So he says, well, you know, I'll get these for you, but you have to hold up the sky while I do that. And so Hercules does, because, you know, he's supposed to be strong. And then Atlas says, oh, actually, you know, he goes against the apples and he says, you know, I've been thinking about it. I don't think I want to take the sky back. I'm going to let you hold it, and I'm going to leave you there with it. And Hercules says, oh, well, you know, that's fine. Just let me put my, he was wearing a cape. I guess people wear capes at the time. He says, okay, let me put my cape behind my neck so it's like a padding. And then if you can hold it for 1 second while I do that, I'll fix it and then I'll take it back. And Atlas is obviously not very smart. He says yes, and you can imagine what happens. Of course, Atlas takes it. Hercules says, man, you are stupid. I can't believe that worked. He takes the apples and leaves. So Atlas is supposed to be basically just his punishment is he has to hold the sky up forever. Obviously, the sky must be enormously heavy. Okay, so the question is, does Atlas do any work? And what do you think? You can think about it for yourself for a second. But the answer is no. According to I guess here the answer is agree. Sorry. Well, the correct answer should be agree. Atlas does not do any work. Why? Because work is force times displacement. Clearly, he is applying enormous amounts of force. None of us could hold up the sky, you know, because it's not really a thing. But even if it was, it would be huge, right? You couldn't hold up that. I'd be saying like, okay, pick up the earth. You know, nobody can do that. But even if you could, you would apply some massive amount of force. But if you're not moving something, then that displacement would be 0. and the total work would be 0. So you see here that work is very different sometimes in physics than it is in everyday life. All right, I might run out of time, so I'm going to go a little faster. Okay, crane lifts a box with a mass of 20 kilograms from the ground to the top of a roof with a height of 10 meters. Crane lifts with a force of 4,000 newtons. Find the net work done by the crane. Well, here we go. What's the force? Well, we're trying to find the work done by the crane, so let's look at the force of the crane, which is 4,000 newtons. Times the displacement. How far does it move? Well, it goes from 0 to 10 meters. Times the cosine of the angle between them. And here's where, I draw pictures. Again, sometimes people want to draw pictures, but I do. And it doesn't have to be elaborate. Here we go. Here's the box. Which way is the force gone? Well, we're trying to lift it up, so the force goes up. And which way is the displacement? Well, he's pulling up and it moves up, it turns out. So they're in the same direction. So what is the angle between these two vectors? Not the angle relative to the x-axis. Be careful. I'm not asking for that. I'm asking the angle relative to each other. And that angle is 0 degrees. The cosine of 0, by the way, is equal to 1. You can punch it in. And so you just end up with 40,000 Newton meters. Simple enough. Again, I would encourage you to pause this right now and see if you can get this one correct. But here we have the work, so I'm assuming you have worked this out now. Work equals force times displacement times cosine theta. So here, okay, we know the amount of work this time, actually. We know it's 200 Newton meters. Times the force. Okay, well, the force we don't know. Times the displacement, which is 50. Times cosine theta. Now, the thing about cosine theta is we don't really know what it is, but I don't think it really matters because we know the total work done. We know the displacement. We really are just looking for at least the component of the force that's the same. So you can say that cosine theta is equal to 1 if you want. And so you would simply divide by 50, and for the force you have 200 divided by 50, and I forgot my calculator, but hopefully I don't mess up. That's 4 newtons. All right. I'm probably going to do another video that'll be kind of short where we talk about friction, and you can see that here, work done by friction, and I'll probably start a new video there. Thanks for watching.